Moving on into chapter 9, we're going to start looking at sets and Venn diagrams. So, by definition, a set is a collection of distinct objects called elements. All right, so a set is a collection of distinct objects called elements or members of the set. All right, we often define sets by listing the elements inside of braces. For example, the set of positive numbers, even numbers less than 10, could be described with the given set here, 2, 4, 6, 8 in the brackets. Or the colors of the rainbow are given here, red, orange, yellow, green, blue, indigo, and violet are examples of sets. Note that the order of the elements in the set does not matter. So, in other words, we usually would prefer to write the set 2, 4, 6, 8 as 2, 4, 6, 8, but we could have it as 4, 8, 6, 2 in a different order. But as long as the elements are the same, we would consider it to be the same set. So let's do an example. Write the set which contains the months of the year. We start with the bracket, all right, and then we have January, February, March, April, May, June, July, August, September, October, November, and December. All right, so there is a set which contains all 12 months of the year. Now, when we work with sets, we have a couple of symbols we're going to introduce. A symbol that kind of looks like a C with the line coming out, almost like an E there, means is an element of. But in math, we oftentimes have definitions for which if it's one, we have the other. So if something is not an element of it, then we do the same letter symbol, but then we're going to put a diagonal through it, which means it is not an element of. And we'll get some examples of this here shortly. So for example, we're going to look at the given set A is equal to 1, 2, 3, 4, 5. Then we could say that 2 is right there. 2 is in the set. So 2 is an element of A, but is 8 in my set? 8 is not in my set, so we would say it's not an element of A. It is possible to have a set that contains no elements. It's written here kind of as the empty or the null set. So it is called the empty set, empty because there's nothing in it. Or we could call it the null set. And the null set is notated as we kind of have a 0 with a line through it saying, hey, we did what was asked, but nothing qualified for the set. Next example, write the set containing all the days of the week starting with the letter Q. Well, none of the days of the week, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, start with the letter Q. So this we could say as the empty set, or we could say it's the null. There's no days of the week that start with the letter Q. If every element of set B is also of set A, we could say that B is a subset of A. Notated B is a subset of A, kind of like a sideways long U there. For example, A is going to be the set of all even numbers, so 2, 4, 6, 8, 10, and so forth. B is a smaller set, 2, 4, 6, 8. Because all of B is part of A, they're all even numbers, then we will describe this as B is a subset of A. Next, we're going to consider the universal set. So the universal set is a set that contains all the elements that we are interested in and is notated with a capital U for universal set. It is defined by the context of the problem we're working on. For example, if I'm discussing students who made an A on the first exam, then the universal set, it would be understood or implied to be the set of my students that we're looking at as we go into the problem. Again, we'll get some more examples of universal sets as we go in and work some more problems. But right now, we're going to continue on with some more definitions for working with sets. All right, next off, we're going to look at unions, intersections, and complements. The union of two sets contains all the elements in either set or in both sets, all right? So if we're interested in the union of sets A and B, we write it with kind of that U symbol, but it doesn't have a vertical line coming back down. All right, so the union means we're looking for all of the x's that are in A or in B, all right? So for example, we're given sets A and B. A is 1, 2, 3, 4, 5. B is 2, 4, 6, 8, 10. To find their union, define A union B. I'm going to go ahead and pick up everything from A, 1, 2, 3, 4, 5. And I also need to merge in everything from B. Well, B has a 2, already got it listed, and a 4, we already have it listed. But B also contributes a 6, 8, and 10. And so this gives us the union here. We took both sets, merged them together. All right. We get another one to practice on. This time A is 4, 6, 8, 12. B is 3, 6, 9, 12. So we need to find A union B. All right, so we got to merge them together. Neither set kind of goes like right in order, so I'm just going to let's put a mark. I'm going to pick up that 3 from B and then 4 from A, and then they each have a 6, so we have a 6 over here, and then 8, 9, 12, and 12. And so this way it's a merger of sets A and B unioned together. All right. Well, another option we have in working with sets and instead of a union is to do an intersection. Now, an intersection is kind of like the opposite. Instead of unioning them together, we're looking for what is in both sets. We're looking for the sets that contains only the elements in both sets. All right. The way we would define it is with an upside down U almost, A intersection B. This means I'm looking for all of the x's such that they're in A and they're in B. They have to be in both. So we're going to go work with sets A and B again. We're going to go find their intersection. So if I were to look at my given set A and B, what's in both? Well, if we go through and look at them, notice that A has 2 and B has 2, so 2 is in both of them. A has 4, B also has 4, and those are the only two numbers that I see that are in both A and in B. What if we took an example where we were looking at people? A has Bob, Joy, Bill, and Sue. Set B has Ray, Bob, Joe, and Sue. So who is listed in both sets? Who makes it in both? Well, in both sets, notice we have Bob listed in both sets. And who else is listed in both sets? Sue. All right, so the intersection, what's common to both sets, is Bob and Sue. All right. The complement of set A contains all the elements of the universal set that are not in set A and is notated A with a little c, kind of almost like an exponent there, to indicate a complement. So what is this? So that means we're looking for all of the x's that are elements of the complement. So they have to be in the universal, but they cannot be in A. So in order to do this problem, we do have to have a universal set. Our universal set we are under consideration is 1, 2, 3, 4, 5, 6. A is the sets 2, 4, 6. So kind of like if we were to say, hey, we already have 2 in a set, we already have 4, and we already have 6. So what's left over? What is not in A from the universal? That'd be 1, 3, and 5. So the complement is what's not in A. It's kind of like you take out A from the universal and what's left over would be A complement. All right, and last definition here for this video, we're going to look at disjoint sets. Disjoint sets are sets that have no elements in common. They have nothing together. So in other words, their intersection is empty. What does A being 1, 3, 5 and B being 2, 4, 6 have in common? Nothing. Their set, their intersection would be the empty set or the null set. All right, so that gets us through kind of a whole bunch of definitions. We'll move over in the next video into getting some examples using our definitions we just went through on sets.